This lecture is part of a series of lectures for Rad229 MRI Signals and Sequences offered in the Department of Radiology at Stanford University. The sixth lecture, MRI Imperfections, Part 2, is broken down into three parts. Lecture-06C covers motion encoding. The learning objectives for this lecture include being able to distinguish between gradient waveforms that compensate for flow and those that encode flow, appreciate the impact of VENC Selection and eddy currents on measures of flow, and to understand the construction of a phase contrast MRI sequence when starting with a gradient echo sequence. You'll recall from the previous lecture that we learned about MR signals and the fact that they're inherently complex valued. And this means that for any image that we acquire on the MR system, it's a function of space. We have pixels at every position. That may be, and the image intensity may also be a function of things like proton density T1 and T2. But fundamentally, the signal is complex valued in that there's some magnitude information that we're generally interested in. This may produce a T1 weighted or a T2 weighted image. But there's phase information as well, and the phase information can be very useful in terms of storing information, which is part of what we'll learn about in this lecture. So in conventional MR, we typically look at magnitude images, and they look something like this. This is a cross-section through the heart, showing a beating heart and blood flowing into the lungs. On the right-hand side is the phase image that corresponds to that magnitude image. And this phase image can be usefully encoded with blood velocity information, which is something that we'll learn about in this lecture. The phase, however, of our complex valued signal can be affected by many components. And we discussed these in the previous lecture. Things like chemical shift, susceptibility, and inhomogeneity can be corrected for or minimized in various ways. We also learned about Maxwell terms that can be corrected for analytically, and then eddy currents, which are a little bit trickier and can be minimized but are still present. We'll talk some about the impact of eddy currents on flow compensated measurements and flow sensitive measurements in this lecture. And finally, in the previous lecture, we learned about how the phase of the signal can be affected by motion and how you can, in fact, design specific gradient waveforms to minimize the phase that arises from motion. So in this lecture, we'll focus on how the phase can be a contribution of an off-resonance or background phase arising from things like susceptibility and off-resonance, other sources of off-resonance, but also a controlled motion phase. So taken together in the last lecture, we saw that the phase that arises from the gradients is related to the integral of the gradient waveform dotted with the spin's position history. So it includes the spin's position at some time zero, its velocity, as well as its acceleration. The acceleration terms are quite small and we can generally disregard them, but the velocity is non-negligible and in fact can be usefully encoded. And so for a 1D example of the above equation, when we combine the off-resonance phase, we can, for example, evaluate the phase for so-called through-plane velocity sensitivity, wherein we see that the phase that we measure in our complex valued MR signal is the superposition of an off-resonance phase that comes from susceptibility and field inhomogeneity. There's a position encoding phase that we use to understand and locate spins at their spatial positions to form images. But we can also control the velocity encoding phase, and this is a dot product of the first moment of the gradient waveform and then the velocity in that direction as well. And here we have in mind a gradient waveform whose first moment is in the z direction, and therefore it will only be sensitive to picking up velocities in the z direction because of the dot product operator. So in principle, we can design this. We can design gradient waveforms to have an M0 to be zero. That is, it doesn't contribute additional M0, and therefore the only M0 is the spatial encoding terms that we use for phase encoding generally. And then we can have another term, which is the first moment term, and we can design this part of the gradient waveform, or this aspect of the gradient waveform, to provide velocity sensitivity. In the previous lecture, we learned about designing M1 to be zero, and we were so-called flow compensated. Here we'll talk a little bit more in detail about how we can design M1 to be non-zero and therefore sensitive to velocity. So when we thought of the flow compensated gradient waveforms last time, we used this as an example of what happens to both stationary spins, that is spins that just reside at their position during the imaging experiment, and then what happens to spins that might be flowing, in particular flowing through a magnetic field gradient. And so when we turn on a magnetic field gradient, we can produce a distribution of spins that's dependent on the position of those spins. And the flowing blood spin does accrue some phase, but it depends on its path. So it depends on how it flowed through that magnetic field, and it will accrue a phase that might look quadratic like this. When we turn on a flow compensated gradient, the design of the flow compensated gradient is such that it has a lobe of area A, a lobe of area 2A, and then a lobe of area A. We sometimes call that a 1-2-1 gradient waveform, or binomial gradient waveform. When we turn on the second gradient waveform, we start unwinding the phase in the stationary spins, and in fact we wind past their original position and add additional phase because of course this gradient waveform is slightly larger in area. But our flowing spin continues to accrue phase, goes past the 0 point, and in fact could go even further past that as it gets into higher and higher areas of the gradient field. And lastly, we turn on this final gradient waveform for a total flow compensated gradient waveform. And what we observe is that regardless of whether the spin was a stationary spin or a flowing blood spin, the net phase imparted on the spin system is 0. And that's a really interesting property and really kind of amazing that we can design gradient waveforms that will be invariant of the underlying velocity. And so what we learned in the last lecture is that the flow compensated phase is the sum of the off resonance phase plus potentially these other terms. But as this was an M0 and an M1 equal to 0, M0 equal to 0, M1 equal to 0 gradient waveform, it meant certain things. It meant that those first two terms would disappear. There's no additional contribution to position or velocity encoding. And we also described that we could ignore the higher order moment terms. You can look at this in more detail mathematically, but for the accelerations we typically see in physiologic circumstances, it does tend to be quite low for the gradient waveforms that we use. And so in fact, this term disappears as well. And so the flow compensated gradient waveform is especially useful for capturing the background off resonance phase, which is useful in particular, as we'll see, when we want to actually estimate tissue velocities. So here's the example that we showed in the last lecture, just showing a magnitude image and the phase image for flow compensated gradient waveform. And this will all make a little bit more sense as the lecture gets into the next section here. But what I want you to notice is that in particular in the aorta here, the phase is relatively flat and relatively uniform, and it's relatively zero valued. It's a little hard to read off of a grayscale in general, but there's no sort of obvious phase distribution in what I'm pointing to, which are known to be blood vessels or areas of flow. And you might identify those same blood vessels and areas of flow as relatively bright areas on the magnitude image on the left. Okay, so that's kind of a quick warm-up to flow compensation. Let's talk more about flow encoding. So in the case of flow encoding, we're going to use a different gradient waveform. Here we're going to use a simple, what we call bipolar gradient waveform. So we'll have a value of, say, an area of negative A followed by an area of A. And so we begin, much as we did with the first part of the flow compensated gradient waveform experiment. We turn on a magnetic field gradient, and that imparts spins as a function of their, imparts phase rather on the spins as a function of their position. And our spin that happens to be flowing through that B field gradient accrues a certain amount of phase. And now we're going to turn the gradient over to have an equal and opposite area, and we'll watch what happens. And what we'll notice is that the phase for the stationary spins realigns. That sort of makes sense. You wound them one way, and then you just unwound them the other way. And as they didn't change position, they ended up with a net zero phase. The flowing spin, on the other hand, does something rather interesting. Whereas it accrued some phase during the first interval of the gradient, and some of that phase was undone during the second lobe of the gradient waveform, we ultimately end up with a non-zero net phase. And the net phase that we end up with is actually linearly proportional to the velocity, which is not immediately obvious until we look at the equations. So here we revisit. the phase for the flow encoding echo, which is still the sum of an off-resonance phase plus some motion sensitive phase. But in this case, I can tell you that this gradient waveform has an M0 of 0, it has no net area, and it has an M1, which is some constant, some non-zero value, if you will. And so in that case, the position encoding term can be ignored, but the M1 term cannot be ignored. And as we said previously, the acceleration terms are not important or don't significantly contribute. And so now we have a flow encoding phase that depends on both off resonance and directly on the dot product of the first moment gradient vector, as well as the velocity of the underlying spin system. And so here's just a careful example of this. So showing the magnitude image on the left, similar to what we saw before, and then the phase image on the right. And the phase image now has more apparent phase information in, again, areas that we know to be flowing blood. And so again, if we focus on the aorta here, you'll see that the phase is going substantially negative, and depending on exactly the direction of encoding, this is either a velocity, say, moving towards the head or moving towards the feet, for example. Here, we're showing that phase only in phase units of plus minus pi, but pretty soon we'll relate those phase units actually in a very linear way to the underlying velocity and show that there's a direct linear mapping of phase to velocity. And you see it in this expression already, that there's a linear mapping, that if the velocity is going up, then the phase is going up, and it's scaled through the first moment of that gradient waveform, so sort of the size of that bipolar gradient. So really a really clever way of encoding velocity information. And a lot of this preliminary work was actually done at Stanford in the 90s. Okay, so quick quiz. You can pause the video if you want to think about this. Flow encoding requires adding a gradient with which of the following? Do we need 0 M0 and non-zero M1, non-zero M0 and non-zero M1, 0 M0 and 0 M1, or non-zero M0 and non-zero M1? And it's quite a mouthful to sort of say all of those things, but given the previous slides, hopefully you're able to determine that we generally want 0 M0 contribution from the velocity sensitizing gradient waveform, but we specifically need a non-zero M1 so that we have some sensitivity to the underlying velocities. So now we have to start thinking to ourselves, how do we pick M1 and how do we design this gradient waveform anyway? And it comes out partly by looking at how we combine the information from this imaging experiment. And so if we have the flow compensated information, which is the sum of, it's just the background off resonance phase, and we have the flow encoding experiment, which gives us phase information related to off resonance and some velocity encoded phase, then algebraically just differencing these two images on a pixel by pixel difference will give us a phase difference map, and that phase difference map will be absent off resonance because the off resonance components or contributions should be the same. And then it depends on the amount of phase, or the phase that will be observed in this velocity map now depends, of course, on the underlying spin velocity and what we call the delta first moment. And so that bipolar encoding uses two non-zero M1s, and that's a slightly different example than the one that we showed, but you can do a flow comp flow encoding experiment, or you can do two flow encoding experiments. And it just changes maybe exactly how you design the M1 into the gradient waveform, but the net delta, the delta M1, is what gives rise to this proportionality between the velocity and the measured phase difference. Okay, so let's look a little bit more carefully at this phase difference term, because it tells us something about our encoding abilities. And importantly, the maximum phase that you could measure is on the interval of plus minus pi, because we're looking at something that's in the complex plane. And as a consequence of that, we can actually define what we call the VENC, or the velocity encoding strength. And the VENC defines the velocity that produces a phase shift of plus or minus pi, and it's simply related to pi being the maximum phase you could encode, and then the delta first moment that you chose. And so when we actually sit and work on an MRI scanner, what we choose is the VENC, and behind the scenes, the scanner will design an appropriate M1 to give you the velocity sensitivity or the velocity encoding strength that you think is appropriate for your experiment. And so here we just see a mapping of both phase and velocity, that as the phase value for the signal that you're sampling is, say, increasing, it's increasing in terms of, say, centimeters per second, but also in terms of, say, pi, until at some point, if we go, say, clockwise and counterclockwise, there's a point at which they measure the same, plus minus pi, but at the same time, those are very different velocities, right? You could be 100 centimeters per second, or you could be minus 100 centimeters per second. So we have to choose our VENC very carefully so that we're not operating in this regime where we can have aliasing, and that gives rise to sort of a confusing velocity estimate. I'll show you an example in just a second. And so here we go. And so here is a similar view that we've seen before. This is the aorta sort of pulsing centrally in the magnitude image. And here we see the aorta pulsing in the phase image. In the phase image, you'll notice a consequence that gives us a longer TE and a longer TR, something that we'll see shortly. It does, in fact, give us high sensitivity. So if the flow, so we can look at the other end of the spectrum, and we could choose a velocity encoding strength to be very, very high. So this is now 9 meters per second, and the clear ability to measure velocities because the dynamic range is so large. And so, as with many things in MR, what's important is to choose something that's well matched to your experiment and sort of in the sweet spot. And so without the aliasing artifact that really challenges our ability to make these measurements. Something I want to get back to is the impact of eddy currents. So we saw those in the eddy current lecture on a few lectures back. And interestingly, in phase contrast, eddy currents can be a really significant problem. And so if we think of the first measurement, this could be the flow compensated measurement, for example, or we think about doing a bipolar encoding experiment. So we could encode with this gradient waveform, which has starts positive and goes negative, and that would have some velocity sensitivity. And then we could do a second experiment where we use this bipolar gradient, and it has an equal and opposite velocity sensitivity. And the delta M1 of these two gradients would give us the M1 that we wanted for a specific VENC, for example. So when we do that first bipolar experiment, we're encoding some phase that includes velocity information. It still includes off-resonance information, and because of these slewing gradients, we'll generate some eddy currents as well. And in the second experiment, we will also measure a velocity that's proportional to the phase. We'll get a similar amount of off-resonance, and we'll also get some eddy current some eddy current phase. Now, what makes this problem especially tricky is that the off-resonance phases will be similar, and that's largely dictated by the echo times. But the phase from the first eddy currents, that is the first bipolar gradient waveform, is very close to equal and opposite. Mathematically, it should be equal and opposite to those generated by a bipolar gradient waveform that's toggled or negated. And so this is especially problematic when it comes to phase difference processing, because when we go to difference these two expressions, if the off-resonance phases are equal, they'll cancel out, but the eddy current phases are equal and opposite, and as a consequence, they'll actually double up. And so we need to have MR systems that have especially small background eddy current phases, otherwise it can lead to considerable measurement errors. And typical systems nowadays probably have an error on the order of 1 to 3% of the velocity encoding strength. And that might seem pretty small, but in fact it can be a substantial measurement error. And so here's, say, a pixel in the aorta, and you can see what its velocity profile looks like. It goes up high, close to our VENC of 150 centimeters per second, and then it falls off. Now, the background eddy current phases may only contribute a velocity of about 1%, so 1 centimeter per second. And you might think that that's not a significant contribution, but oftentimes for understanding cardiovascular physiology, what we may want to know is the flow, and the flow is milliliters, which we have to get from our centimeters per second estimates. And that requires adding up pixels over a region of interest, say the whole aorta. So we're adding up over space, we're multiplying by the area of each pixel, and then we're actually integrating over time as well, so that we can capture the velocity information that informs us about flow during the entire cardiac cycle. And so as a consequence of adding up over space and integrating over time, these eddy current effects can actually compound and give us errors of flow or volume that are on the order of 10 or even 20%. So you can think of it in terms of integrating this, what looks like small eddy current curve, but because we're integrating it for the entire cycle, it can actually contribute a significant amount of volume, erroneous volume, to the total estimate. Okay, so lastly, let's think about how the phase contrast sequence comes together. This is a spoiled gradient echo sequence. Just to orient you, this is the excitation pulse that's used for slice selection. We do some phase encoding, readout prephaser, and then a readout gradient that helps us form the gradient echo. And then we're going to spoil the transverse magnetization before exciting again. And we saw previously that to generate a flow compensated sequence, we would have to add a large upright gradient here, and that would ensure that from excitation to echo that we had zero moment and 0 first moment. But the timing here was poorly chosen because it overlaps with the formation of our echo. And so we stretched things out a little bit to make room for everything. And so the flow compensated gradient echo sequence has a TE and a TR that's about 5 or 15% longer depending on a few parameters. So that extends things a bit already. What happens in the case of the flow sensitive measurement? On the flow sensitive measurement, we have to include a bipolar gradient that maybe looks something like this. And we've already stretched things out as we did previously so that we can accommodate the addition of this bipolar gradient for velocity sensitivity before we're trying to read out and form echoes. And in this case, we want the added gradient to have zero moment and some non-zero first moment so that it's actually velocity sensitive. And now if we actually want to composite both of these things back to back, then we can do the phase difference experiment. And so we acquire one flow compensated echo and we follow that with one flow encoded echo. And because these are relatively near in time, we expect most components to be very, very similar and allows for subtraction of the background off resonance phase and sensitivity to the velocity phase. Now, the consequence of building up this phase contrast sequence is that the TE and TR are extended to accommodate sort of the combination of flow compensation and flow encoding. And then even more so, we need 2 TRs to measure the phase difference, thereby correcting for off resonance. Okay, so one last question before we wrap up the lecture. So when it comes to flow measurements, which of the following does not directly impact phase contrast velocity measurements? Is it the choice of VENC? Is it eddy current background phase? Is it the off resonance phase? Or is it the longer TE and TR that we require in this sequence? So you can pause while you think about your answer. And here I'm suggesting it's the off resonance phase that is not impacting our velocity measurements because it differences out in the phase difference processing. And so we do need to carefully choose our VENC to avoid aliasing. We do concern ourselves with eddy currents because they can lead to velocity and flow offsets. And the longer TE and TR is problematic, obviously because of the extended scan time, but a longer TE generally decreases your signal to noise. And so you may lose a little bit of velocity sensitivity because of that. So in summary, we've described how gradient waveforms can be designed to compensate for flow or encode for flow. We've talked about the VENC selection and how it determines velocity sensitivity and velocity aliasing. We've also described how eddy currents double up in phase contrast imaging and corrupt measures of flow. And finally, we've seen that adding flow compensation and flow sensitivity to a gradient echo sequence extends the TE and TR, and of course requires 2 acquisitions, thereby extending the acquisition interval. These are 2 terrific texts that I used to develop some of the material here and are very good references for further learning. Thank you for joining us for Rad229 again, and please click the links below for additional lectures.